Hi everyone, welcome to JD Does Dev. I'm JD, and today we're going to be talking about Docksal and Docker. This is part one in a series of videos getting you introduced to Docker and Docksal. So let's get started. In this training, we're going to be talking about a few things. We're going to have a brief overview of Docker. So if you're familiar with Docker, stick around, you might learn something new. If not, then you definitely want to check this out. After that, we're going to have an intro to Docksal, get into what we need to get started actually using Docksal, and then towards the end we'll have a couple of fun scenarios that we can run through. Now before we begin, I do have a request that you have a basic understanding of programming concepts. A lot of stuff will make more sense as we get into it if you know what's going on there. Hopefully you've been using the command line a little bit, have some familiarity with using terminal. If you're running a Windows or Mac, then have VirtualBox, Docker for Mac, or Docker for Windows installed before you get started. So if you don't have those installed, go ahead and pause this and come back. And if you are running this on a Linux machine, make sure that you have Docker installed. And it also helps if you have a GitHub account, because some of the code will be available on GitHub in a repo. Links will be down in the descriptions. So let's get started on Docker. What is Docker? Well, in a high-level overview, Docker is built on Linux containers. At a high level, this means that Docker runs on top of the host machine's operating system kernel. A Linux container is a packaged application that includes everything it needs to run. Since it's contained within its own container, the app is extremely portable and easily testable, which makes it really useful and valuable to developers and DevOps specialists. But what is Docker? Well, it provides an environment and workflow for the Linux containers. Think of it as a container coordinator, or a system for the containers to make things happen. It accommodates the containers, creates a welcoming environment for them, keeps them working in sync, and prevents them from running rampant across your system. Docker is also available for multiple systems and architectures, including Mac, Windows, many Linux distributions. AWS runs some Docker stuff. Google Cloud has it. There's quite a few others that I haven't listed. Let's get in a little bit to how Docker works. What's going on behind the curtain? Well, Docker is built on multiple components. We've got the Docker client, the Docker daemon, Docker images, Docker containers, and storage. So let's go over those a little bit. The Docker client. This is responsible for everything that containers do. There are Docker clients available for most common operating systems, including Mac, Windows, and all of them that I mentioned before. It could either be on the same host as the daemon, or it can connect to a remote daemon. Now, if you're not familiar with daemon, it's a term for a long-running program, something that starts up and you just let it go. It also provides a CLI, or command line interface, to start, stop, build, and execute commands within the containers. Now, it's mainly used for pulling in images and running them on the host. Now, the daemon itself is where the magic really starts to happen. This is where applications and containers are able to run. Images, containers live there, volumes are defined, networks are connected, all the stuff happens there. The Docker client sends commands to the daemon via the REST API calls or direct interaction. Now, images are blueprints for containers. An image itself is often defined by no more than a single file, usually some form of a Docker file. This file gives the image instructions on what it needs to run. So let's go ahead and put together our own image. All right, so let's switch over to our terminal here. We don't need a full text editor for this. A terminal will be just fine. Now what we're going to do is create a Docker file, and we're going to put that in this folder here, projects, Docksal training, Docker. All right, if you're running this on a Windows machine, put it wherever the file goes. This does work for Mac and Linux though. So if you don't know how to do that, let's go ahead and do it. We're going to start from our home directory. We're going to make there are projects. which already exists on mine. Then within there, we're going to make the directory Docksal Training Docker. Again, it already exists on mine, so that's why we're getting that error. All right, so let's get into that. Clear the screen out. So what we're going to do now is create our Docker file. We're going to do that by creating the file itself using touch Docker file. Check in here. And there it is. Docker file is available. All right. Now we're going to open it up in our favorite text editor. If you're using terminal, easy enough to use Vim, Emacs, or Nano, whichever is comfortable for you. Or if you want to open it up in VS Code or whatever, that's fine too. So, Vim Docker file. Here we go. And here's what we're going to put in it. From Ubuntu, run echo hello world, because this wouldn't be a tutorial video if we didn't have hello world somewhere in it, right? We'll save that, exit. Now this file is using another image, Ubuntu, and it's building off of that to create its own image. The only thing this image will do is create a container using Docker's CLI image, then echo the words hello world in the build output. Nothing too fancy, but we'll see a lot happen. So let's build it and see where it goes. Clear. So this command does a couple things here. We've got Docker build, which tells Docker that we're going to build an image here. We're going to tag it so that it doesn't just have a random hash and it's hard to read. Image example 1.0.0, ready for release. And this is just to make sure that we tell it the correct folder. This comes out to where we are now. It's the same as running pwd in the command line, or for us, it's going to be users, username, then here. Let's do that. Okay, and it worked. So if you look, it doesn't really seem like a lot, but let's break it down. So we're going to start with our command. Docker build tag image example 1.0.0. Tells Docker we're building the image, we're tagging it, and we're using it from the current folder. Now the next line here, sending build context to Docker daemon. Your file size here may be different than mine, and that's fine. This is what we were talking about before with the Docker client. It primarily communicates with the Docker daemon. That's what this line is doing. It's sending from the command line back to the Docker daemon. Hey, this is what we want to do. Now, step 1 of 2 from Ubuntu. This is what we had in the Docker file. Now, Docker is reaching out to the internet looking for an image named Ubuntu, and it's pulling it down. If this is your first time using Docker or the first time pulling this file down or this image down, then you're going to see a lot more in here. It's going to have downloaded and waiting and all kinds of things, but that's fine. That's what we're expecting. Then step 2 here is run echo hello world. Used cache, went through, and successfully built. Then we tagged it down here. So things went well, right? We have an image, but what does an image actually do? What's next in it? Well, this is where we get into containers. So a container is a self-contained application that runs on a shared kernel. Docker containers are no different. They're just like Linux containers. When you run an image, you're creating a container that has followed all the instructions in your Docker file. Now let's look at our Docker file again. Pretty simple. All of these instructions here, all 2 of them, from Ubuntu, run echo hello world. Now a Docker file can be this, something very small, just a line of code that spouts out hello world. Or it can be something much more robust. It can be a fully functional operating system with everything that somebody might need to develop a complex application in compiled language and have stuff to test it. But there are a few things that I would like you to note. One, a container is not permanent. If that container is removed, all the data that's not in the image is destroyed. Two, a container is portable. By sharing an image or a Docker file to build an image, a container can be recreated identically anywhere Docker can be found. You can send a Docker file to anybody who has Docker, they can run the command, and they'll have exactly the same as you. 3, a container is only as powerful as its host. It wouldn't be a good idea to try running, high-speed, high-resource games on a Docker container. 3, a container is only as powerful as its host. It wouldn't be a good idea to try running a containerized version of a graphical operating system on a Raspberry Pi Zero. 4, a container is limited by what is in the image. There will be no more or no less functionality than what is in the Docker file or other image definition. We're only pulling down the base Ubuntu, and we're telling it to echo hello world. That's it. Now, in contrast to a virtual machine, a container is much smaller and easier to spin up. Usually it only takes a matter of seconds. Now that we've talked about images and containers, how do we convert an image to a container? How do we use an image to form a container? I'm going to exit out of Vim here. Clear the terminal. So let's take this image and run this command. Docker run -i-t, and just to make it cleaner, we're going to go on multiple lines. Name equals test container. Image example 1.0.0 bin bash. All right, now this is going to start up the container and allow us to use the command line from within it. So we're using that container we built from our image, and we're actually starting it up. And if you look, here we are. Let's do a quick check, and you can see, yes, here's everything that you'd expect to see in a Linux machine, right? Got our boot, dev, etc, all this stuff. So we have Ubuntu here. So go ahead, pause the video, take a couple seconds to poke around if you want to. If not, we're going to move on to Docker storage. So let's talk about storage. When we talked about containers, we mentioned that a container is volatile. It means if you stop it, you lose everything that's not in the image the next time you start it back up. This can be painful if you're working on a containerized project that might take more than a day. It could be something big, something that's shared. And if your computer decides to update and reboot without warning, and for some reason this container gets removed, then you've lost all your work. Docker gets around this by using volumes and bind mounts. So a volume is persistent storage for a Docker container, whereas a bind mount is binding a directory on your host machine to a container, similar to a symlink, but a little bit different. So let's look at volumes a bit. Let's go back to our terminal, and we're going to create a volume. Now, the advantage to a volume is that it can be easily wrapped up with a container, and it can be portable with an image, meaning that you can put everything together, the image and the volume, and ship it or share it around. To create a volume, we need to define it, and we do that by running docker volume create, and we're going to name it example. All right, so we got that back. Now, if we look at what volumes are available, we're going to use this command, docker volume ls. We can see that we have the volume example there. However, this doesn't do a lot other than reserve some storage on your host for the volume. What we really want to do is have this volume mounted to a container. Now we do this by using the docker run mount command. So let's clear our screen here. And we're going to run a very similar command to the one before. So docker run it And again, just to make things a little bit cleaner, we're going to separate it onto different lines. We're going to name it example container. And now we're going to use mount. Source is going to be example volume, which is a new volume, and target is going to be app. Now the target is where the volume is mounted to within the container. So when you go in and look around, we'll see an app folder there. That is where the volume lives. Now we also are going to name which image we want to use, Ubuntu, and we're going to run bin bash. Now something that I didn't mention before is this line here. We've got two flags, the I, the T. Now the I flag says that we want to open this container up as interactive, and the T says we want to interact with it through the terminal. Okay, so that's how we were able to get in and poke around earlier. Let's run this. We're here. Wonderful. Let's take a look. And you can see we've got everything that we were expecting, right? Full file system, the full application. And now we have this folder here, app. So let's do a little experiment. So we are going to create a couple files here. Clear the screen. Now we are going to echo test volume file and send that to app test. That's a file it's going to live in. All right. And next we're going to do similar. Echo test container file and throw that into our home folder, which in this case is root container test. All right, now let's just see if these files exist. We could do that by running cat app test, and that's what we've got. And we can also check the container file by running cat container test. And that's exactly what we were expecting to see, right? Now let's step out of our container here by typing exit. That stops it, and we're going to remove it. We can do that by docker container remove example container. All right, so it's gone. We're going to check to make sure docker container ls, and yeah, nothing there. Now let's run that command that we did before to get the container started with the volume. Okay, see everything here exactly the same. I just went back to the previous command, running that, and we're in. Okay, everything looks good. We do a little bit better view there. We've got everything we were expecting. Now we're going to first look to see if our app or if our volume test file is there. So cat app test, and it's there. We're able to see it. Now the other one we created, cat container test, doesn't exist. The test container file is gone forever because we removed the container and everything within it disappeared. So let's go ahead, exit this container and remove it. We're done with it. You can see how volumes kind of work now, right? Pretty awesome, huh? Now there's one more thing I'd like to mention before we get off of Docker storage, and those are NFS volumes. An NFS volume is similar to a bind mount and a volume, but it's slightly different in that an NFS volume allows you to connect through an NFS share to a folder on the host machine. Now, different operating systems have different uses for this, and it depends on which operating system you're using, whether or not you want to use this or the default. For example, on Docker for Mac, NFS is a little bit faster than the default OS X FS, which is specific to Mac. Docker for Windows, NFS is going to be faster than Samba, which is the default there. But if you're using Windows subsystem for Linux on Docker, a bind mount is going to be faster than NFS. All right, up next we're going to be talking about Docker services. Now, sometimes it makes sense to wrap up a few containers to work together. For example, if we don't want to put too much on a single container to handle database, a web server, networking, etc., we can create services in place of standard containers. Docksal relies on services extensively to create various stacks. Services are often part of a larger application where containers usually stand on their own. One of the main advantages of services compared to containers is that the pieces can easily be swapped out. Let's say that we wanted to move hosting providers for our web application. Provider A uses Apache and PHP 7.2. Provider B uses Nginx and PHP 7.3. We could just push everything up to Provider B and hope that it works, but with services, we can create custom local environments that match everything on Provider B and make the changes locally. This way, we feel confident when we would deploy, knowing that our application works well inside the hosting environment. Many of the functions of services are beyond the scope of this training. However, a few things that should be noted are Docker services are defined individually as part of a larger application. Docker services are structured in Docker files. However, they're managed by Docker Compose, which is a utility that interacts with an entire application rather than a single container. Applications that use services are defined in a YAML file, that's .yml, often named dockercompose.yaml, with several services defined along with settings and information to help everything run together. The Docker docs have many examples of using services, and something that we'll cover more in the Configuring Docksal section later on. Now, Docker registries are something that are pretty important. A registry is where images are stored. The most common of these is Docker Hub, which is at hub.docker.com. This is normally where custom Docker files pull images down from to build custom images. Docker Hub allows you to search for both official and unofficial images to be used in your project, extended into a custom image, or studied to see how the whale sausage is made. However, I don't condone the hunting of whales for the making of whale sausage. Whales are beautiful, endangered creatures. It's possible to add custom registries or even private registries to your Docker setup, but that's also outside the scope of this training. Check the Docker docs. They have all the information you might need on that. Now, a big question that a lot of people might be asking is, why containerize? Well, here's why. For the purposes of this portion of the training, a local dev environment refers to anything that lives on your computer storage, like MAMP, WAMP, local PHP, local Apache, etc. Now, the key advantages to containerization are reusability, portability, and configurability. Let's dive into those a little bit. Reusability. For your local dev environment, it requires additional setup for each project. This means that a developer using one of the AMP stacks or local services need to make sure that when they're working on a project, their settings match where the project will be hosted or eventually live. Changing these settings can be time-consuming and tedious. Virtual machines are reusable, but they're far more resource-intensive than containerization because they create an entire virtual machine for each instance. Those virtual machines represent everything from the hardware, the kernel, software, drivers, and every other aspect of a machine with each new virtual machine that is spun up. Multiple VMs or virtual machines on a single computer can take up a large chunk of your resources. Now, containerized dev environments can be reused on multiple systems for multiple users and for multiple projects. This means that no matter where a project is loaded, it will have the same setup as everywhere else from the initial install. Configuration time is minimal compared to the other setups. Now, as far as portability goes, for a local dev environment, it's usually not portable at all. It requires a setup on each machine where a project will live, which means developer A's machine will have to have the same setup as developer B, otherwise developer B won't be able to easily work on the same project. On a virtual machine, it's portable, but different virtual machine setups can require that a developer download additional tools depending on which virtualized environment is being used in the project. Now, containerized dev environments are completely portable and only require that a developer have Docker installed on their system. This eliminates the need to keep multiple VM tools up to date or multiple versions of the same service on your host machine storage. Configurability for local dev environments, traditionally they've been pretty difficult to configure on a per project basis. Virtual machines are highly configurable, but time-consuming to remove and recreate a VM with changed settings. Containerized dev environments are highly configurable and fast to update, often only taking seconds to recreate an environment, even after significant changes since only the affected containers need to be updated and not the entire project. Now, let's go a little bit further beyond just Docker. Why should we use more than just plain vanilla Docker? Now, if we think about our Docker Basics section, we can see what setting up a project can entail. Now, for a vanilla Docker project, we have to find a base image, we have to add the steps in a Docker file, we need to build that image, decide if we're going to be using a volume, bind mount, NFS volume, or something completely different. We spin up the container, we verify that everything works, we ensure that everything is set up so we don't lose data in the container. Now, these steps are not difficult with some practice, but there are many tools that eliminate this setup, allowing you to begin development faster, and they take a lot of the guesswork out of spinning up your application. Now, there are several advantages to using a tool that uses Docker as opposed to just vanilla Docker. With a tool like Docksal, most of the setup is taken out of the equation and you can begin developing faster. Oftentimes, most commands are wrapped up into a handy command so that long commands like docker container exec mycontainer bash -lc or www vendor bin drush and stage file proxy, which is a Drupal command, that can be handled in a more intuitive and less verbose manner. In addition, tools like Docksal take all the guesswork out of deciding whether your application should exist in a single container across multiple services that work together. They handle the orchestration between services out of the box so that you can get straight to developing. And these tools are often developed, maintained, and contributed to by many developers who are passionate about a project and want to build on it to see it grow. This means that if you're running into a problem, there's a good chance that others have already run into the same problem, and there will be an answer waiting for you. Unfortunately, rolling a custom solution does not give you the same advantages. You're potentially stuck with a community of one. Now, you can check out the partial list of contributors to the Docksal project, the Docksal credits page, which is at docs.docksal.io/credits. Up next, we're going to begin our intro to Docksal and actually get into working with it. Thanks for watching. I hope you learned something. I know I sure did. If there's something else that you'd like to see me cover, be sure to leave a comment down below. Don't forget to like and subscribe to this channel for more videos. Look forward to seeing you on the next one.